So while this isn't a chapter in and of itself in the textbook, I think it's important enough to dedicate a separate video to this idea, and we're going to be talking about something called the TNB frame. And frame in this use is just another word for like a coordinate system. So a frame is like a coordinate system. Right, like the X, Y, and Z axes could be considered like the X, Y, Z frame that we use to express functions in 3D. So far, we've looked at two different principal unit vectors for vector-valued functions. So for a curve R of t, right, that's a curve in space. We've looked at two principal unit vectors for these curves. And they are, first, we looked at the unit tangent vector, t. So the unit tangent vector. And that one kind of described the direction the curve was going. So it told us the direction of motion. Right, it always points in the direction the curve, the particle along the curve is heading. And then the second one we looked at in the last video was the unit normal vector, and that was capital N's. And this one told us the way the curve was turning. So it points in the direction of turning. And we know that T and N, right, T and N are always orthogonal to each other. So T and N are always, right, by definition, and the formulas force them to always be orthogonal. And then we know that in 3 space, so in R3, you can have up to 3 unique vectors that are orthogonal to each other. So we have 2 so far, and in this video we're going to explore the third one. So the third one is the unit binormal vector, and it's called the binormal vector, right? It's because it's normal to 2 other vectors. So binormal means normal to both t and n. So if I were to just draw a picture over here, I might say that at this point here, we have a unit tangent vector pointing in this direction. We know the unit normal vector would point in that direction, right in the direction of turning. And then if we had another vector orthogonal to both, it's binormal, then we would have the unit binormal vector. And in this case, it would be pointing, it's kind of hard to draw, but it would be pointing straight up like that, where it's orthogonal to that one and orthogonal to n. So it's pointing kind of up and out of the page, if that makes sense. And so the unit binormal vector, what it tells us is the unit binormal vector that we call capital B. It kind of tells us how the particle is twisting about its axis. So it's this the B vector, which is kind of the most conceptually hard to understand, is telling us about how the particle or the curve is twisting through space. So T tells us the direction of motion, N tells us the direction of turning, and B kind of tells us this tendency for it to twist as it moves through space. And so knowing that the b vector, the unit binormal vector, is normal to both t and n, you should be able to construct from everything we already know what the formula for b is. So if we ever have two vectors, t and n, and we need to find a third vector that's orthogonal, mutually orthogonal to both of those, then we have an operation that allows us to do that. And in that case, it's the cross product. So the formula for b is the unit binormal vector is equal to t crossed with n. And we know that we don't have to divide it by its magnitude. We don't have to divide by the magnitude of t cross n because t and n are already unit vectors. So t cross n will also be a unit vector. Right, and so that's how we get a third mutually orthogonal vector to t and n. And so there's some really neat applications of this, and you can imagine that as the point of evaluation that we're looking at changes, all three of these vectors change too. They all stay of length 1, but their directions are changing, right? And so I have a cool animation here that will show, as we travel along a curve through space, how these three principal unit vectors change. And so it should be, yeah, so right here, we can see that this particle is traveling through space, represented by the black dot. So the black dot is like the point of evaluation along this red curve. And then we have the blue vector is the unit tangent vector, and it's always pointing in the direction of motion. The green vector is the unit normal vector, and it's pointing in the direction that curve is turning at that point. And then the new one we learned about is the unit binormal vector, normal to both of those, and that one is pointing, and it tells us about how the curve is twisting at that point. And you can see that as we travel along, all three of them stay mutually orthogonal to each other. And so, just like we have the global coordinate system with the x, y, and z, we also have this local coordinate system that travels with us. So this t, n, and b vectors, let me just write this out. Right, so t, n, and b form a local coordinate system at every point. So we have this big unchanging global coordinate system with x, y, and z, and then for every specific point on a unique curve R, there's a unique local coordinate system that changes with us. And so that's going to be useful in the next couple sections for breaking down components of acceleration or components of force into this local coordinate system. And we'll see how that's useful. One of the big applications is to aerospace engineering. So if you're ever familiar with airplanes or flying a plane, you might be familiar with the three principal axes on an airplane. Let me just draw a little picture here. So if I have an airplane, let's see the best I can draw it. So there's the back, and we have one wing coming out here, another wing there. Can I get rid of, there we go. So we have our little airplane with the cockpit. Then we can superimpose these t, n, and b vectors onto it. So you can imagine that I'll draw its flight path in red. So here's its path of motion. Maybe. So that's kind of like r of t, its path of travel. Then we can evaluate the plane as if it was like at this point right here. So that's the point we're evaluating at. Then we can draw its unit tangent vector, which would be like this. So there's t. Its unit normal vector would be coming out like this. And then its specific unit binormal vector would be pointing right straight up. Oops. And so all these are orthogonal to each other, just like that. And like I was mentioning, if you're familiar with how to fly a plane at all, you may have heard of roll, pitch, and yaw. So those are the three axes with freedom of movement to control the plane. So there's roll, pitch, and yaw. And so roll is movement or rotation around the unit tangent vector. So how do I draw this? So let me pick this purple. So roll is a rotation of the plane around this vector, right? Pitch, right, is the angle that the plane is flying, right? So if the head is higher than the tail, that's rotation around the unit normal axis. So this is pitch. And then yaw is its side-to-side movement, which is rotation around the unit binormal axis. And so this is yaw. And so in flight school and learning how to fly a plane, you learn about these three principal axes that are the TNB frame, a local coordinate system that can help you navigate flight. Another unique thing about the TNB frame is there's the characteristics frame, or characteristic planes. It should actually be planes formed by the TNB vectors. So just like for our global coordinate system, we have like three planes: the XY plane, we have the XZ plane, and we have the ZY plane. Right, so there are three characteristic frames to the XYZ coordinate system. Similarly, on the TNB frame, there are three planes as well. So let me write those here. So here are three unit vectors, T, N, and B. Then this plane formed down here by the T and N vectors, I'll draw that in yellow. So this plane is called the osculating plane. And it's called the osculating plane because osculating is the Latin word for kissing, and this is like a tangent plane that just is tangent and kisses the curve at that point. Then let me pick another flavor. So this plane, formed by B and N, the B and N vectors form the normal plane. And then the vectors T and B, they form the T and B vectors form the rectifying plane. And so a very common question related to these unit vectors is, here's a curve R of t, find the equation of the osculating plane, or the rectifying plane, or the normal plane. And so the equation of that plane, on this example, would be the equation of the plane that passes through this point here and contains the n and t vectors. So in this case, if n and t lie in this yellow plane, that would be the osculating plane. Now you know from chapter 12 that to write the equation of any plane, you always need a point and a normal vector. And so to write the equation of this osculating plane, what would you use as the normal vector in your plane equation? Well, to write the osculating plane, you would use the b vector. The unit binormal vector would be the normal vector to the osculating plane. And then for the rectifying plane, you would use the n vector, and for a normal plane equation, the t vector. Those would be the ones that would be the respective normal vectors. Okay, so let's look at example 1. It's asking us to find the t, n, and b unit vectors and the equation of the osculating plane for the following curve at the point t equals 0. So, we have r of t is cosine ti plus sine tj plus tk. So you should already be familiar with this equation. This one should be very familiar to you. It is the curve equation for our helix. And this is one that you should know cold, one that you should be able to picture in your head. So it's this one right here. And we're asked to evaluate at t equals 0, which if we plug in 0 into our position function, we get 1i plus 0j plus 0t, or plus 0k, which means we're evaluating at this point. So just from the onset, without doing any calculations, I should be able to guess that our vectors, our t, n, and b vectors, should look like t should be pointing in just the j direction, n should be pointing in the negative I direction, and B should be pointing in the Z direction. So my prediction is those are going to be the equations, and then the osculating plane should kind of look like this. It should be pretty flat and should kind of be containing the t and n vectors at that point. So these are my predictions. Let's do the actual calculations right now. So remember, to find the unit tangent vector, that is going to be the velocity function divided by its magnitude. So let's find v. So the velocity function is going to be the first derivative of position, which gives us negative sine ti plus cosine tj plus just 1k. The magnitude of that is going to be the square root of sine squared plus cosine squared plus 1, which is the square root of 2. So I'm just going to do that in my head. So that's the square root of 2. And so that we know the t vector now, the unit tangent vector, is going to be first derivative divided by its magnitude. So in this case, it will be negative sine t over the square root of 2i plus cosine t divided by the square root of 2 j plus 1 over square root of 2 k. So there is our unit tangent vector. So now I'll switch flavors here and we'll do what's next? N. So now we'll find n. And that is equal to the derivative of the unit tangent function divided by its magnitude. So we'll get t prime is going to be negative, what is that, cosine t, isn't that right? Negative sine of t becomes negative cosine t divided by the square root of 2i minus sine of t over square root of 2 j plus 0k. So we'll get 0k. Now the magnitude of t is going to be the square root of, what is that? 1 Yeah, so I'll square the denominators first and just get 1/2 cosine squared t plus 1/2 sine squared t. And I'll factor out the 1/2 to get 1/2 times cosine squared plus sine squared is 1. So you just get the square root of 1/2, which is just 1 over the root 2. So there's the magnitude. And now we're just going to divide the derivative of the unit tangent vector function by the magnitude of the unit tangent vector function. So in this case, we get n will equal negative cosine t divided by the square root of 2, all divided by 1 over the square root of 2. So that those square roots actually just cancel out, or they divide out, excuse me, and you get negative cosine t I, and then the exact same thing will happen here, and you get minus sine t j. Perfect. So there's our normal vector. And now we can let's evaluate these at the point we're trying to find, so the specific point. So I'll do t, our t function, evaluated at 0, is going to be negative sine of 0 divided by the square root of 2, so that's just 0, plus cosine, so I'm evaluating this function up here, right, at 0. So you'll get cosine of 0 is 1 divided by the square root of 2, so you get 1 over root 2 in the j direction. And the reason I'm evaluating these now is because it'll be easier to do the cross product to find the unit binormal vector if, instead of doing the generic functions, you do the specific one for the point you're looking at. So I'm just finding the specific vectors we're going to cross first. And then plugging in 0 to the k, you still just get 1 over square root 2k. And then we know n, let's evaluate the n vector at 0. So n at t equals 0 becomes negative 1i plus, yeah, I believe that becomes 0j, so it's just negative 1i. So now let's find the unit binormal vector. So to find b, that's going to be t cross n, and because now we have the specific vectors for this point, we're just going to cross t and n. So in this case, that ends up being, right, we get our 3x3 matrix with I, j, k, 1 over square root 2, excuse me, that's in the j direction, so we get 0, 1 over root 2, 1 over root 2, and then we get negative 1, 0, 0, right? And I'll save the computation of that because it's just doing cofactor expansion. But that becomes negative 1 over root 2 in the j direction plus 1 over root 2 in the k direction. So there's our specific unit binormal vector, right? So that's our b vector at t equals 0. So let me just formalize this over here real quick. So our t, a, and b vectors at t equals 0, right, t is 1 over root 2j, 1 over root 2k, n at t equals 0 is just negative I, and b at t equals 0 is negative square root of 2 j plus 1 over square root of 2 k. And now the last question we're asked is to find the equation of the osculating plane. Look, there's so many mistakes in this worksheet. All right, the osculating plane. So the osculating plane is that plane formed by that contains the t and n vectors that we use the unit binormal vector as its normal vector. And so so to write the osculating plane, I'll do that over here. So here we'll do the osculating plane. So the two things we always need to write a plane equation are a point and a normal vector. So the point we'll use is just r of 0, right, at t equals 0, the position function evaluated at t equals 0, which becomes the point 1, 0, 0. Right, I just plugged in 0 into our position function. And now we need the normal vector. So for our normal vector, we're just going to use the binormal vector, which will be negative 1 over square root of 2 in the j direction, plus 1 over square root of 2 in the k direction. And now let's plug those into our plane equation. So the plane equation is a x minus x naught plus b y minus y naught plus c z minus z naught equals 0, where a, b, and c are the components of your normal vector, and x naught, y naught, z naught are your point that you're evaluating the plane at. So let's plug those in to get the specific plane equation. We'll get 0 times x minus x naught. So there's 0, times x minus 1 plus, actually minus, 1 over square root of 2 times y minus 0 plus 1 over square root of 2 times z minus 0 equals 0. So to simplify this, we end up just getting, what does that become? Negative 1 over square root of 2 y plus 1 over square root of 2 z equals 0. And then I believe we could simplify this even further. Oh, yeah, just multiply each side by negative 1 over square root of 2. So that just becomes y minus z equals 0. So that's the equation of the osculating plane. So let's just osculating plane equation at t equals 0. Yay, we found it. It's very computationally heavy to get through these, but definitely nothing beyond our capacity. And so that is the TNB frame.